Okay, so today let's do some problems that are concerned with rectification, right? And so is there any question from rectification before we start? Okay, if there is no question, then we'll start. If there is any, just feel free to stop me in between and you may ask the questions. So let's start with question 1. We have a rectified output of a sinusoidal signal generator is connected across a resistor R, which has a resistance of 1.5 kilo ohms, right? Let me just mute this. Okay, yeah. So here the rectified output is, so they have already mentioned that the output has been rectified. So the output has already passed through a rectifier, right? And then it is coming into this resistor R. And the variation of time T of the potential difference V across R is shown in this figure. The graph also tells you that there is rectification already done. And what kind of rectification is this? It's a half wave rectification, right? So state how the rectification that is shown in this figure may be achieved. How can we achieve rectification? Anyone?
By using diodes.
Exactly, right? So you use is, now you have to be more specific because this is half wave rectification, and we know that that is achieved by one diode, right? Not a combination of diodes, not a bridge rectifier. So use a single diode. And how do you use it? How do you connect it? So to achieve half wave rectification, you have to connect it in series, right? So you can connect, suppose if the output was not rectified, then the rectification would happen over here. It would be connected in series with this resistor R, right? So you use the single diode in series with R. Right? So it's clear, right? No questions?
Yes.
Now, a capacitor is now connected in parallel with resistor R. The resulting variation with time t of the potential difference V across R is also shown. So here you can see this is smoothing has been done, right? So again, they have said already that the capacitor is connected. This is the output that you would expect for a capacitor connected in a circuit where rectification is happening. Use this figure to determine the mean potential difference across resistor R. So what do you think would be the mean value of the potential difference across R? What is the peak value of potential?
6 volts.
Okay, so it is this line. So let's extend it. 6 volts, right? Okay. So how do I find the mean potential difference? What do they mean by mean potential difference?
The average.
The average of you're right. So how do we calculate that? V.r.m.s is equal to V naught divided by under root 2. Actually, that's not how you will do it. You have to use the figure to do it. So what we can do is, they're saying that use this figure, right? So where do you think the average would lie? For example, let me just draw a sine function. If this is my graph for some sine function, where does the average lie? Suppose this is the
0.
time axis, right? Yeah, so it lies at the time axis for this particular graph. The average is 0 and it lies on this line, right? Halfway between the two. In exactly the same case, same way, the average over here would lie halfway between this. So it would be somewhere around about here. If I can draw it neatly, something like that, right? Which is approximately
Sir,
5.4.
can't we
Yeah,
just take the range, like the least value and the highest value, and then divide that by 2?
exactly, right? So yes, you can do that. But so in this case, you don't, the least value is what? This is the maximum value, right? Which is 6 volts. And the least value, where will you measure that from?
4.8
This line,
here.
right? So it would be this line, right? So that is approximately, if you do that that way as well, you'll still get approximately 5.4 volts, right? So is that clear?
Yes.
So you can do it this way, or exactly in what way that you suggested. It would be 6.0 plus 4.8 divided by 2, which is 5.4 volts. Right. So now the mean current in the resistor. So we know what resistor is. Resistor was 1 kilo ohms, right? 1 kilo ohms, that is 1000 ohms. We know they're asking mean current. Mean current corresponds to mean voltage or mean potential, which we have found out. So let's call it mean, let's give this symbol, is 5.4, right? So how do I find the current? I just use this is mean current times R. And then mean current would be just mean voltage over R. So the mean voltage is 5.4. The resistance, I think it was not 1 kilo ohms. What was it? I think it was 1.5, right? Yeah, 1.5 kilo ohms. So it would be 1500. 1.5. Let's change that here as well. Okay, so this would be 1500 ohms. And the math gives you 3.6 milliamperes, so into 10 raised to power minus 3 amps. So that's the mean current. Any questions till this point? Okay. So now the time in each cycle during which the capacitor discharges through the resistor. What would be the time in each cycle when the capacitor is discharging through the resistor that I have connected across it? When is the capacitor discharging? If you look at this graph, which line or which part of the graph, basically region, defines that the capacitor is discharging?
Where it's sloping downward.
That it's sloping downwards, right? So it should be starting from here. It is this distance. Let me label it on this axis like this. So up until this point. If I know this time, this is the time for which in one cycle for which the capacitor is discharging. So that is about 0.02 7 seconds. So is that clear?
Yes.
Okay. 0.0 what was it? 27, right? 27 seconds. Okay, so let's move forward. Now, using your answers in part I, calculate the charge passing through the resistor during one discharge of the capacitor. So we want to compute the charge that passes through one discharge. One discharge means that uh, the time the charge is taking to flow is this 0.027, because this is one discharge cycle, right? And the current is the mean current, which is 3.6 into 10 raised to power minus 3. And we know that the current is defined as the rate of flow of charge. So from here, the charge is just the product of current and time. So you just have to use your values for the mean current, which is 3.6 into 10 raised to power minus 3 amps times the time for one discharge cycle. So it's for one discharge, so it's 0.027 seconds. Right? And this will give you the charge of 9.72 into 10 raised to power minus 5 coulombs. Was that clear?
Yes.
Okay. So next, we just have to compute the capacitance of the capacitor. We have everything with us now. We have Q, we have V, we have I, we have R. All these variables are known. We want to find C. If you want to find C, the capacitance, we'll just use the first principal equation of capacitor, which is Q is equal to C times V, right? So from this, C is just the ratio of charge to the potential difference across the plates, which is straightforward because the charge is 9.72 into 10 raised to power minus 5, and the potential difference was 1.2. 1.2 for the capacitor. What would be the potential difference? Remember, this potential difference is across the resistor R, right? So, but now we're finding the capacitance of the capacitor for which we need the potential difference across the capacitor, right? So what would be the potential difference across the capacitor? We know the potential difference across this is 5.4.
The peak voltage minus this.
The peak voltage, which is 6.0 volts, minus 5.4 volts. Okay, but why would you say that?
Because a voltage gets divided in series.
Okay, but when you connect the capacitor across resistor, do you do it in series or do you do it in parallel?
Oh, if it's in parallel, then it's also going to be 5.4.
It's going to be 5.4 volts, right? Because you connect the capacitor in parallel when you want smoothing, right? So let's go back here, and it would be 5 point. What was it? 5.4, right? So that is 1.8 into 10 raised to power minus 5. What is this? Farad. Okay, is that clear?
Yes.
All right. Okay. So let's move to the next problem. Here we have a sinusoidal alternating voltage, which is to be rectified. Suggest one advantage of full wave rectification as compared with half wave rectification. What's the advantage? Why do we move from, you remember we started from half wave rectification, but that did not fulfill our purpose, right? So we wanted full wave rectification, and then we proceeded a bit further by adding a capacitor in parallel to smooth it out. So what was the advantage of going to full wave rectification? There was less loss in potential, right? Compared to half wave rectification. Do you remember? Right. So what does that mean? If there is less loss, so you can say something like there is less loss of potential, or you could say that if there is less loss of potential to the circuit, the advantage is that there will be a higher output power, right? Because the potential drop, the potential loss is minimized. So because from P is equal to V times I, the output power will be more compared to the half wave rectification. So is that clear?
Yes.
Okay. Now the rectification is produced using the circuit, this thing. So this is a bridge rectifier attached to a resistor, and here is the alternating current. All diodes may be considered to be ideal. The variation with time t of the alternating voltage applied to the circuit is shown before the rectification happens. This is the graph for this part only, the alternating current that's going. And so they've shown, given us two figures for that. It's just given so because we'll mark, we have to mark on these figures, draw on these figures separately. So on the axis of figure 7.2, draw a graph to show the variation with time t of the potential difference across diode A. So let's go back. Across diode A, what would happen to the potential difference? Okay, so let's assume, so here our current starts, moves in this direction first. This is first direction, and then we'll flip the direction and check as well. So it goes here, it cannot go in this part, so it goes over here, then it goes over here. It cannot again go in this part because the diode restricts it, and so it goes over here, and then it reaches the resistor R. Well and good. Now let's flip the current. So this is the current. Now the current goes over here, it goes over here, and then it goes over here, and then it goes to the resistor R. So what is happening is, if we just want in the second part, when you flip the direction of the current, no current passes through diode A. So if I have to draw it for diode A, there is only current passing in one direction, and on the other direction, no current passes through diode A. Although the current is passing to the resistor from the second direction of the current, but they have specifically mentioned that do it for diode A. So for diode A, in one of the direction, the current flows, but in the other direction, no current reaches diode A. So what type of rectification would that be? So it's something like, so for the first direction of current, let me actually, we're going to draw it on the axis as well, but just let's do it once over here. So for the first direction, it's like this, it goes, but when the direction of current is about to flip, no current flows through diode A. So it's zero. So it's this line on this line. And then again, it changes direction. So the current flows again. And then after that, again, it's zero, which is a half wave rectification, right? So the half wave rectification is happening across diode A. So on this figure, if I have to draw on 7.2, I'll draw something like, let's use a different color. This, and then you'll draw this. Right. So is that understood?
Why are we talking about diode A here?
Okay, so because in this first part of the problem, they say that draw a graph to show variation with time t across diode A. Right? They specifically mentioned that use one of those figures for diode A, and then the other one they're saying use it for diode B, right? Second part.
Okay, got it.
Okay, right. Okay, just can you give me like 2 minutes? I'll just be right back.
Sure.
Okay. Okay, let's continue. Okay, now on the axis, is everyone here? Can you hear me?
Yes.
Okay, so now on the axis of figure 7.3, draw a graph to show variation with across diode B of potential, right? So let's go back. Okay, so for diode B, what happens? Okay, if the current flows in this direction, the upwards direction, it goes like this, goes through A and goes directly to the resistor R, does not go through diode B. When the current flows in the opposite direction, now again, remember the current has flipped direction. So can you first tell me what, when the current flips its direction, what happens to the phase angle? What is the phase difference between the two waves? So if this is the graph, actually, you can just look at this graph.
180 phase.
This graph. Yeah, exactly. So it's 180, right? So is that understood by everyone? So it starts from 0, goes here, goes back to 0. Now when the current flips its direction, so you can see that the difference between this part and this part is of a total 180-degree flip, right? So you would expect now for diode B to have a 180-degree flip, because everything else is the same. The current, if, for example, for diode A, if the current was in one particular direction, so we had it in this way, up in on the up part of the graph. Now it's just going through diode B, but the current has flipped direction. It goes through diode B and then goes back to R. So everything is still the same, except for the fact that the current has flipped its direction. So there is still half-wave rectification because it's only passing through one diode. And we know half-wave rectification is achieved when you just use one single diode. So the only difference will be a flip of 180 degrees to this thing. So for this part where the direction is upwards, the upwards direction is used, no current is flowing through diode B, right? You can see when it's upwards, it goes here, it goes here, does not go through B, just goes there. Now, when it's downwards, then it goes through diode B. So downwards, you will get something. And then again upwards, so you'll get 0. Then again downwards, you'll go like this. And then again upwards, 0. And then downwards again. Okay, so is that clear?
Yes.
All right. Now, okay. Now on figure 7.1, draw the symbol for a capacitor connected into the circuit so as to provide smoothing. So figure 7.1 is this. Where do I connect the capacitor to provide smoothing? So you just have to remember that you connect it in
Parallel with resistor.
Parallel with resistor R. So you can draw it over here. Label it as C. So this is how you'll connect the capacitor, and this is how you can save some of the loss in a potential drop, which is called smoothing. So is that clear?
Yes.
Okay. Now next, figure 7.4 shows the variation with time t of a smoothed potential difference across the resistor R. So now the smoothing is done when the capacitor was connected. So this is how the graph looks like. State how the amount of smoothing may be increased. How can we increase the amount of smoothing?
By providing a higher
So by
providing a high
sorry.
voltage.
Okay, the voltage is not in our control, right? So the voltage is coming from the AC supply. It's not in our control. But there is something. What do we do to do smoothing? We add a capacitor, right? So that is in our control. We can add a capacitor to our circuit to smooth out the voltage. And if I have a capacitor that is capable of storing more energy, so it will store more potential, and the smoothing will then be more increased. There would be less drop in this. This drop would significantly decrease, right? So it could be, instead of this, it could be like this. Because now there is less loss in potential because more of it is now stored in the capacitor. So you can use it from the capacitor. It's stored inside, and so there will be less loss in it, in the potential. Does that make sense? Okay, so how can you do that? You can just say at least that you increase capacitance. One way of doing that is by connecting another capacitor in parallel with the first one. Why in parallel?
Because capacitance is added up when they're in parallel.
Capacitance is added, exactly, right? So, or you could just use a higher one, a single capacitor with a higher value of capacitance. So it depends on the situation. If you don't have a higher capacitor, then you just connect them in parallels to get a higher value. But anyways, is that clear? Any questions?
No, it's clear.
Okay. Okay, question number 3. We have a bridge rectifier and it consists of 4 ideal diodes A, B, C, and D. Here you can see them. An alternating supply is applied between the terminals X and Y. We have a variation with time t of the potential difference V across the load resistor R, and it's shown. So if you look at this graph, this is the graph that you would expect for a bridge rectifier, right? Because the bridge rectifier provides full wave rectification. So this is the graph for that. Now the load resistor R has a resistance 2700 that is provided. The peak value of voltage is also given. You can see it from the graph. That's plus 4 volts. So use the figure 6.2 to determine the mean power dissipated in the resistor R. So again, mean power dissipated is P is equal to mean VI, right? So if I go back to the graph, I need to look for the mean value for voltage. What would that be? Anyone?
2.
It would be 2 volts. Would it be? It would be 2. Yeah, of course it would be 2, right? So it would be halfway between this. So it is 2 volts. So that is the mean potential drop. And okay, so we don't have I, but we have a resistor, 2700 ohms. So we can use this thing that mean power is mean voltage squared over R, right? And this would be 2.0 squared over what was R, 2700.